The last thing we're going to look at is non-singular matrices. And here, where it's really just a review of what we've already talked about, we're just sort of changing our frame of reference to a matrix versus working with a number of vectors. So if we take those vectors, put them into a matrix, then we can talk about whether or not the column vectors within that particular matrix are linearly independent again. So we're really doing the same thing. Again, we're just doing it in the context of it being inside of a matrix. So we start with an n by n matrix, and it's going to be non-singular if and only if the zero vector is the only solution to the homogeneous equation. So this seems exactly like what our definition for linear independence was, because it is. And what we're really talking about is that the column vectors of A are linearly dependent if and only if the trivial solution is the only solution. So we can actually use our previous vectors that we had as an example of this. And we'll just grab those vectors. And put them into a matrix A. So 1, 2, 3, 2, -1, 4, and 0, 5, 2. And we already determined that this set of vectors was linearly dependent, and that's okay. It just means that the matrix A then would be called singular. And if we wanted to make a non-singular matrix, then we could maybe swap out that third column for something else. I'll just put in 1, 1, 1. And if you were to row ref that, you would find out that that's going to end up being the trivial solution only for the homogeneous equation. So again, by our definition, this is now non-singular. It's a little counterintuitive in the sense that when we only get one solution, we refer to the matrix as non-singular, and if we get infinitely many solutions to the homogeneous equation, we refer to the matrix as singular. So you'll have to get used to that counterintuitive terminology in this particular case, just kind of the way it was decided for some reason. So that's our singular and non-singular matrices. Again, in principle, it's really the same. We're just looking to see whether or not the column vectors of the matrix are linearly independent or dependent. And again, if it's just a bunch of vectors, we refer to them as linearly independent or linearly dependent. If those vectors are inside of a larger matrix, we refer to them that as singular or non-singular, depending on the situation. So now let's take a look at the last piece, which is Theorem 13. And what this says for us is if we take a matrix that's n by n, and we're doing this inside of Rn, so the square matrix n by n matches the size of the space, then the equation Ax equals b has a unique solution for all the column matrices B, if and only if A is a non-singular matrix. So this particular statement is really just a guarantee, if you will, that we get solutions for any B as long as A is a non-singular matrix. We can kind of look at an example of this as well. And I'll use kind of a semi-obvious one. We're going to take the unit vectors E1, E2, and E3. And in this context, they are E1, E2, and E3. I know you guys are used to a different notation for those unit vectors. You can think of them as I, J, and K. These vectors are linearly independent. If you were to put them into an augmented matrix with the homogeneous solutions, it would be pretty clear that the only solution here is the trivial solution, because that bottom row tells us that x3 is equal to 0, so we don't get a choice there. The second row says x2 equals 0. We don't get a choice there. And the top row says that x1 is equal to 0. So the only solution we get out of that is, in fact, the trivial solution. So very quickly, we were able to show that these three vectors are linearly independent. And what we want to then do is kind of show that for every vector in R3 in this case, because these are all in R3. So for every vector in R3, we want to show that we can write it as a linear combination of E1, E2, and E3. And again, we can do a quick example of this by grabbing any random vector here. So I'll just take 3, 5, 1 maybe. And we'll write that as a linear combination of E1, E2, and E3. And it's going to be some constant A times E1 plus some constant times E2 plus some constant times E3. And it's not going to be hard for us to figure out pretty quickly without doing a whole lot of work that A is going to have to be 3, B is going to have to be 5, and C is going to have to be 1. And that's just a consequence of the fact that we're working with this E1, E2, and E3. So it makes it a lot easier to determine what those coefficients are. We can do that quickly. The point here is really just to emphasize this theorem. It says if you've got 3, say, linearly independent vectors in R3, we can generate any vector that we want on that. And it would be true for other size spaces as well. If I have 2 linearly independent vectors in R2, then you can generate any vector in R2 from those 2 just by taking linear combinations. 4 linearly independent vectors in R4 would generate all the vectors in R4 just by taking multiples of them or linear combinations of them. So that's really what this theorem is saying. There's just a couple extra notes that I'll just throw on here just to finish it off. And note 1 here is just that a set of vectors is linearly dependent if and only if at least one of the vectors is a linear combination of the others. And if you've been following our discussion, then that should make perfect sense. The second note, any set of vectors that contains the 0 vector is linearly dependent. And 3, the third note, and we kind of already showed this, the unit vectors are linearly independent. And we showed that for the case of R3, where we had that E1, E2, and E3, but it would be true for unit vectors in any n-dimensional space. So those are the last of the notes. There's a problem or two here for you to practice some of those concepts on and see how that goes.